Welcome to the deep dive. Every single day, we collectively generate just an absolutely staggering amount of data. I mean, think about it. Every click, every sensor reading, every transaction, the volume is, well, frankly, it's mind-boggling. But the real challenge isn't just creating it, right? It's making sense of it all quickly, consistently, and without breaking the bank. So for us today, the central question really is, how do we store, organize, and process this enormous flood of information to actually get valuable, actionable insights? Okay, so a foundational concept that's become really widespread in tackling this is the data lake. Just imagine like a central, boundless repository, usually in the cloud, where you can just dump massive amounts of varied data, all sorts of sources. And data lakes, they brilliantly solve many of the raw storage problems. I mean, they're incredibly cheap, super scalable. But here's the crucial catch. When you want that raw data, maybe unstructured or semi-structured, to behave like, traditional database tables, with that reliability, consistency, the ability to update records you'd expect, well, plain file storage just isn't enough on its own. It's like having a library full of books, right? But no card catalog, no borrowing system, maybe no way to update a book without rewriting the whole thing. It just doesn't work for complex tasks.
Exactly. And that's precisely why data lake table formats emerged. These aren't just new file types, they're really a crucial intelligent layer built directly on top of your raw data files, which are typically sitting in cloud object storage like Amazon S3 or similar. And the sophisticated layer, that's what brings those much needed database-like features to your data lake. Most notably, we're talking ACID properties. That's atomicity, consistency, isolation, and durability. Crucial stuff. And just as importantly, the ability to update, insert, or even delete individual records within these massive data sets, almost like they were living, breathing tables.
Right, giving structure and reliability to the chaos. And today, we're really embarking on a mission to cut through the noise here. We're diving deep into the three titans in this space. Delta Lake, Apache Hudi, and Apache Iceberg. Each one has kind of carved out its own niche, built on a unique philosophy, gathered a fiercely loyal following. So our mission for this deep dive is to unpack the core designs of these formats. We'll compare their performance across the operations you probably care about most, loading data, updating it, querying it, and ultimately help you pinpoint which one might be the unsung hero for your specific data challenges.
Okay, let's unpack this.
Great. So let's start by digging a little deeper into why simply storing files in cloud object stores like S3 falls short for complex analytics. I mean, while these stores are incredibly cheap and scalable, fundamentally they function as pretty simple key value stores. And this means they inherently lack built-in transactional guarantees. So for instance, imagine you're trying to update, say, a customer's record that spans multiple data files, a single logical operation. There's just no inherent atomicity. So a reader, someone querying the data, could potentially see a partial update. Some parts old, some parts new, messy. And if your data ingestion job crashes midway, rolling back those inconsistent changes becomes incredibly difficult. You're looking at potential data corruption.
Wow, yeah. So just updating a record can leave your data in a really messy state. That's a huge problem. And it's not just about consistency, is it? There are significant performance challenges too, right? Especially for really large tables, millions of files sometimes. Like imagine trying to get a list of all the files in a massive table from S3. That list operation, it only returns what, like 1,000 keys per call?
That's right, up to 1,000.
So for millions of files, this could literally take minutes, which dramatically slows down query planning because your system first has to figure out which files to even look at before it can start the actual query. It almost makes you wonder how anyone managed large data lakes before these formats came along.
Well, they face challenges.
Yeah, and this is exactly why Delta Lake, for example, was developed by Databricks to directly tackle these pervasive issues. Data corruption, painful performance, the works.
Right. And what's truly fascinating here is how these fundamental limitations of simple file storage really created a desperate need for a new abstraction layer. Traditional file formats like Parquet and ORC, they're excellent for columnar data storage, great compression, but they're inherently immutable.
Meaning you can't change them once written?
Exactly. So this design means if you need to update or delete even a single record, you often have to rewrite the entire underlying file. When we talk about write amplification in copy on write, just imagine you change one tiny bit of info in a huge document. Copy on write often means you have to rewrite the entire document. That's the amplification. Way more data gets written than just the change itself.
Okay, got it.
And that process is not only inefficient, computationally and I/O-wise, but it can also become quite costly, especially when you're dealing with petabyte scale data.
So if plain S3 is fantastic for cheap storage but falls short on reliability, consistency, speed for those complex analytical needs, what's the answer? This is where our three main contenders really enter the arena, each taking a unique swing at these challenges. First up, we have Delta Lake. Initially developed by Databricks, now open source, it's an ACD table storage layer using a transaction log. Very robust. Then there's Apache Hudi. This one was born out of Uber's incredibly demanding needs for transactions and efficient data management. Massive, real-time data lakes, handling lots of updates quickly.
Yeah, high-frequency updates were key for them.
Right. And finally, Apache Iceberg. Developed by folks at Netflix and Apple, it was specifically designed to overcome those cloud storage scale problems we just discussed, especially slow file listings and metadata management for truly colossal data sets.
And it's important for you to understand, these formats don't invent entirely new file types from scratch. Instead, they build upon common big data file formats. Those things like Apache Parquet and ORC. These are industry standards.
Columnar, compressed, great for analytics.
Exactly. Column-oriented, compression, super efficient storage, blazing fast analytical queries. Some, like Hudi, also support row-oriented formats like Avro for certain use cases, but Parquet and ORC are the main players. The real innovation with Delta Lake, Hudi, and Iceberg isn't in reinventing the wheel with new file types. It's in that intelligent layer above these files. That's the layer that adds all those database-like features we need: transactions, schema management, updates.
Okay, now that we understand the core problems they solve and the foundation they're built on, the real deep dive begins when we look under the hood. Because while they all aim to bring database-like features to your data lake, they each take a fundamentally different path in how they achieve it, starting with maybe the most critical piece: how they handle transactions. This is where it gets really interesting because these design choices, they profoundly impact performance and features.
Absolutely. To ensure those critical asset-y properties, each system has a distinct approach. Take Delta Lake, for example. It achieves its rock-solid reliability by cleverly leveraging inherent atomic features of your cloud storage itself, like put-if apps and operations. Or it can use external battle-tested services like AWS DynamoDB to manage its transaction log.
So it relies on other proven systems for that atomicity.
Pretty much. Think of it as a super reliable ledger, meticulously recording every single change. That's what gives you those strong consistency guarantees like you'd expect from a traditional database. It even provides incredibly robust isolation levels, like serializability in many configurations.
Okay, and how does that contrast with, say, Hudi and Iceberg?
Well, Apache Hudi and Apache Iceberg often use table-level locks. These might be implemented via systems like the Apache Hive Metastore or maybe Zookeeper.
So more like a gatekeeper for the whole table during changes.
Kind of, yeah. Now, while this approach works, some of the source material highlights that Hive Metastore locks might not always provide the absolute strongest guarantees. There's potential, perhaps under heavy contention, for issues like dirty writes if those locks time out prematurely. It's a trade-off. But it is worth noting all three formats do utilize optimistic concurrency control, so they check for conflicts before committing changes, which helps mitigate a lot of potential issues.
Makes sense. What about managing all the metadata? You mentioned listing files is slow. How do they speed that up?
Right. Efficiently managing metadata is absolutely crucial for query performance. It's the key to bypassing those painfully slow object store list operations. Delta Lake and Apache Hudi both store their metadata essentially in a tabular format. Delta uses its transaction log, which gets periodically compacted into Parquet and JSON checkpoints for efficiency. Hudi uses a dedicated metadata table, optimized for its needs. And the cool thing is, both of these can query their own metadata using distributed processing engines, like Spark.
Ah, so they use the same tools that query the data to query the metadata?
Exactly. Which means it scales really well for extremely large tables. Delta Lake, for instance, has shown benchmarks with like 7 to 12 times performance improvement for tables with hundreds of thousands of files just by using this distributed metadata approach.
Okay, and Iceberg, does it do the same thing?
Iceberg takes a different path here. It uses a hierarchical structure of manifest files to track the data files. Think of it like a tree. The sources we looked at indicate that Iceberg, at least currently in its client libraries, tends to process this metadata tree on a single node.
A single machine?
Yeah, within the query planning phase. Now, this can actually be blazing fast for smaller or moderately sized tables because you avoid the overhead of distributed coordination. But it does have a potential scaling ceiling for truly massive data sets, petabytes with millions or billions of files.
So for extreme scale, that single node processing could become a bottleneck.
It's a possibility, yeah. In those scenarios, you might find Delta Lake or Hudi's distributed metadata processing gives you more headroom, helps prevent those dreaded metadata bottlenecks.
Interesting trade-offs there. Let's move on to how these systems handle changes, specifically data updates. You hear about copy on write and merge on read. Can you break those down?
Sure, these are the two primary approaches, copy on write or CowW and merge on read more. With copy on write, CowW, when data needs to be updated, the affected files, the entire files containing the records to be changed, are completely rewritten into new files.
Okay, so you copy the existing data, make the change, and write a whole new file.
Essentially, yes. As we discussed, this incurs higher write amplification because you're copying and writing potentially much more data than just the changes themselves.
Right.
But the big upside is that reads are straightforward and typically very fast. There's no read amplification because the data files always represent a clean, consistent snapshot. No merging needed at read time. Delta Lake primarily uses this CowW approach, and both Hudi and Iceberg also offer CowW table types.
And this is good for...
Generally well-suited for read-heavy analytical workloads, where you're doing a lot more querying than you are updating data frequently.
Okay, so what about the other one, merge on read?
Right, merge on read more operates quite differently. Instead of rewriting entire base files, only the changes, the updates or deletes, often called deltas, are written to new, separate delta files.
Ah, so you keep the original file and just write the changes separately.
Exactly. The actual merging of this base data and these delta files happens later, at query time when you go to read the data. This approach is significantly more write efficient. It lowers the cost and latency of writes, enabling much more frequent updates. Fantastic for near real-time scenarios where data is constantly streaming in and changing.
But there's a catch, right?
The trade-off, is that it can increase read costs or read latency because the system has to perform that merge operation, combining base and delta files on the fly during the query execution.
So faster writes, potentially slower reads.
That's the core trade-off.
Mm-hmm.
And Apache Hudi and Apache Iceberg both offer merge on read as an option, giving you that flexibility depending on whether your workload is more write-intensive or read-intensive.
Okay, that makes sense. CowW for read speed, more for write speed.
Generally speaking, yeah.
So now let's get to the performance benchmarks.
Yeah.
How do these actually stack up against each other in practice? You mentioned some academic papers looked into this.
Yes, there are a couple of key studies. One called A Performance Comparison of Data Lake Table Formats from Loom UFRGS, and another from the CIDR conference titled Analyzing and Comparing Lakehouse Storage Systems. These studies use Apache Spark on Amazon EMR, simulating common data lake workloads to compare Delta, Hudi, and Iceberg. So let's start with loading data, getting massive amounts into the lake for the first time. Here, the Loom UFRGS paper found that Apache Iceberg generally pulled ahead of the others in their tests. Delta Lake was usually close behind, pretty performant too. Apache Hudi, interestingly, was significantly slower in these bulk load scenarios, sometimes more than double Delta Lake's time.
Double. Wow.
Yeah. The CIDR paper also found Hudi to be much slower, like 10x slower for bulk loads. They explained it's really optimized for keyed upserts, those smaller targeted updates or inserts based on a key, not massive initial ingestion. Hudi apparently performs some expensive pre-processing during loading that impacts bulk speed.
Okay, so Iceberg wins on initial load, Delta close second, Hudi lags. But what about querying? That's often what matters most day to day. Is it the same story?
Here's where it gets interesting. A bit of a twist. Both papers consistently found that Apache Hudi generally outperformed Delta Lake and Iceberg in query speed in many scenarios.
Wait, Hudi was faster for queries even though it was slower to load?
In many cases, yes. Especially, it seems, on smaller, more selective queries. The Loom UFRGS study, for example, showed Hudi outperforming in almost all the TPCDS benchmark queries they ran. The CIDR paper noted Delta was faster overall across their broader query set, but they also acknowledged Hudi's strong performance on smaller queries. They attributed this partly to things like cached query plans in Hudi and its efficiency in handling tables with frequent small updates.
So maybe Hudi's optimizations for updates also help certain query patterns.
That could be part of it. The CIDR paper also gave some reasons for Delta's general speed advantage on larger queries, like targeting larger file sizes by default, which reduces I/O and improves compression. And they noted Iceberg's custom Parquet reader in Spark was actually a bit slower than Spark's default reader in their tests, which might have held Iceberg back slightly on queries in that specific setup.
Fascinating. So query performance is really nuanced. What about updates? Changing existing data.
Right, the update phase. Here, the Loom UFRGS paper found that Delta Lake generally had the best overall execution times for the update workloads they tested, the fastest end-to-end. However, they also observed that Apache Iceberg showed the greatest speed up as more worker nodes were added to the cluster during the update phase.
Meaning Iceberg scaled better for updates?
It suggests better scalability for updates in that particular scenario,
Hmm.
yes. As they threw more hardware at it, Iceberg's update performance improved more dramatically than the others.
And Hudi.
Apache Hudi often demonstrated the worst performance in the update phase of these specific benchmarks. Again, reinforcing the idea that its strengths might lie more in those frequent, smaller, near real-time upserts rather than large batch updates, which these benchmarks likely focused on.
So what does this all mean then? It's crystal clear there's no single winner across the board. Not even close. What these benchmarks really tell us isn't which one is best, period. It's more like which one shines when. If you're doing massive initial data loads, Iceberg often looks good.
Seems so.
For reliable, reasonably fast batch updates, Delta seems to lead consistently.
Often, yes.
But then, surprisingly, for certain kinds of analytical queries, especially maybe on frequently changing data, Hudi can pull ahead.
It appears so in these tests.
It proves that even a perceived underdog in one area can have distinct advantages elsewhere. It really is about picking the right tool for your specific job, your workload profile.
Precisely. And it's crucial to remember these are benchmarks. Synthetic workloads.
Hmm.
Your real-world mileage can and likely will vary significantly depending on your actual data, your specific queries, your cluster configuration, your cloud provider, everything.
Yeah, good point. As one source aptly put it, you could probably tweak any benchmark to make any of the three systems look best if you wanted to.
That's often the case with benchmarks.
Okay, so beyond pure performance numbers, what about other critical features? Things that might sway your decision regardless of raw speed.
Absolutely. These features are equally important, sometimes more so, for practical use. For example, all three formats, Delta, Hudi, and Iceberg, support time travel.
Being able to query the past.
Exactly. It allows you to query past states of your data, maybe to see what a cable looked like yesterday or last week. This feature is invaluable for debugging data pipelines, for rigorous auditing purposes, or for training machine learning models using precise historical snapshots of your data. It's a game changer compared to traditional file systems.
Yeah, time travel sounds incredibly useful. What else?
All three also support schema evolution. This means you can change the structure of your table over time, add new columns, maybe remove old ones, change data types without needing to rewrite all your existing historical data. Huge flexibility.
That's essential as business needs change.
Definitely. But Iceberg goes a step further here with a feature called partition evolution.
Okay, what's that?
So all formats let you evolve your schema, add a column, etc. But Iceberg's partition evolution lets you change how your data is physically organized or partitioned on disk for new data without messing up the partitioning of your old data.
Ah, so if I initially partitioned by month, but now want to partition new data by day.
Iceberg lets you do that seamlessly. You change the partitioning scheme for data written from now on, but the old monthly partitions remain valid and queryable alongside the new daily ones. You just have to rewrite everything just because your partitioning strategy evolved. It offers incredible flexibility.
That sounds powerful. Any other unique optimization features?
Well, for data layout optimization, Delta Lake offers something pretty clever called Z-ordering. Imagine your data points have multiple dimensions, like location, time, and maybe product ID. Z-ordering physically groups data points on disk that are close to each other across all those dimensions combined.
Sort of clustering related data together.
Exactly, but in a multi-dimensional way. The benefit is when you query for a specific slice of data, say sales for a specific product in a specific region during a specific week. Because related data is co-located, the query engine can very efficiently skip over huge chunks of data that aren't relevant. Delta claims this can lead to massive data skipping, like 90% plus in some real-world security use cases, making selective queries lightning fast.
Wow, skipping 90% of the data scan is huge.
It can be. Apache Hudi, for its part, provides a similar concept with its clustering features, allowing for flexible data layout adjustments to optimize query performance too.
Okay, lots of powerful features beyond just ACID. This raises a really important question then. Which format should you, the listener, choose for your specific use case? Especially thinking about the booming world of AI and machine learning, where data demands are just constantly evolving and growing.
That's the million-dollar question, isn't it? For AML workloads, the good news is all three formats successfully address those critical needs we've discussed. ACID transactions for reliability, historical data tracking via time travel, and massive scalability. But the best fit depends on the specifics of your ML workflow. If you're doing large-scale batch processing, maybe training models on huge historical data sets, and you need advanced metadata management and robust time travel, Apache Iceberg is often seen as an ideal fit. Its design handles massive scale well for batch reads. A Delta Lake, on the other hand, really shines for real-time or streaming AML workloads. Think online inference, or models that need to be updated frequently with new data. Its strong AC guarantees and incremental data processing capabilities are crucial there. Plus, its deep integration with Apache Spark is often a significant advantage in ML ecosystems.
Makes sense, Spark being so dominant in ML.
Right. And Apache Hudi excels if your primary need is handling high-frequency updates within a real-time streaming AML context. Maybe you're constantly updating feature stores based on user activity. Hudi gives you more fine-grained control over data ingestion and updates, making it particularly strong for change data capture, or CDC, pipelines, where you're mirroring changes from operational databases into the lake for ML use cases.
It's helpful to connect this to the real world. You see these formats being used by some of the biggest, most data-intensive companies out there, right? It's a testament to their power and necessity.
That's absolutely right. These aren't just theoretical constructs. They're powering massive operations. Companies like Uber and Walmart leverage Apache Hudi extensively for their huge, near real-time data lakes. Particularly for those high-frequency CDC workloads we just mentioned, getting data changes reflected quickly. Netflix famously developed and uses Apache Iceberg to handle its entire analytics stack. Everything from recommendation engines to content delivery optimization relies on it.
Billions of events a day, probably.
Easily. And of course, Databricks customers make heavy use of Delta Lake. Databricks reports that something like over 70% of bytes written by their customers go into Delta Lake tables across a huge array of use cases. Even Apple has contributed significantly to Iceberg, recognizing the need for efficient and reliable data lakes at their scale. And beyond typical analytics, Delta Lake is proving crucial in specialized fields too, like information security, managing petabyte-scale security logs where that Z-ordering data skipping can offer huge speedups, or in bioinformatics, for processing massive genomic datasets where benchmarks have shown up to 100x speedups in specific genomic query scenarios using Delta.
So when we look at the current industry sentiment, adoption trends, it's fascinating. There's a lot of buzz. Many folks in the data engineering community seem to view Iceberg as gaining significant momentum, maybe even, quote, winning the open format war. But you mentioned true open source for Iceberg earlier. Delta Lake and Hudi are also open source projects under Apache or Linux Foundation governance. What's the critical distinction there? Why does that true label get applied to Iceberg, and why does it seem to matter so much to the community?
Yeah, that's an astute observation and a really important point in the current landscape. While all three are technically open source, Iceberg's community structure and governance model are often perceived as being more truly vendor neutral. Contributions come from a very diverse group of major players. You've got AWS, Snowflake, Apple, Google, Dremio, Tabular, and yes, even Databricks itself heavily involved.
So not dominated by a single company's initial vision.
That's the perception, yeah. This diverse contribution base fosters broader collaboration and perhaps reduces the feeling of being tied to a single vendor's ecosystem or roadmap, even if that vendor is committed to open source. This true open source nature, combined with that broad support from major cloud vendors, is definitely a key factor in its momentum. For instance, AWS recently launched managed Iceberg tables within their S3 service, promising things like automatic optimization and potentially 3x faster query performance compared to running unmanaged Iceberg tables yourself. That kind of platform commitment is significant.
That is significant. And what's maybe even more interesting, and perhaps a sign of where things are heading, is that Databricks, the main force behind Delta Lake, is also deeply integrating Iceberg, specifically Iceberg v3 support. This new Iceberg version brings major new features, right? Like deletion vectors for efficient row-level deletes.
Right, much more efficient than rewriting whole files for small deletes.
Yeah.
Also row lineage, better support for semi-structured data types, even geospatial types, really powerful additions.
And the fact that Databricks is embracing this competitor's format, it really hints at a potential unification of the data layer, doesn't it? Where maybe these formats become more interoperable, allowing you to use Delta features on Iceberg tables or vice versa, all built on Parquet and Spark.
It certainly points in that direction. Increased interoperability seems to be a major goal across the ecosystem now. It's like the formats are starting to speak each other's languages more fluently.
And the benefit of that for the user.
The profound benefit of all these open formats, and especially this move towards interoperability, cannot be overstated. It boils down to no vendor lock-in. You truly own your data, stored in an open format on commodity storage. You should be able to easily switch between different compute engines, Spark, Flink, Trino, Snowflake, BigQuery, or even move between cloud providers without having to go through painful, expensive data migrations.
Freedom and flexibility.
Exactly. This fosters what people are calling an interoperable, composable, and efficient, or ICE data stack. It's a major driving force behind the whole burgeoning data lakehouse market, combining the best of data lakes and data warehouses.
Okay, so wrapping this up.
Ultimately, as we've explored today, there really is no single best data lake table format for every single use case out there. Each one, Delta Lake, Apache Hudi, Apache Iceberg, has unique strengths, design philosophies, and ideal scenarios. It really depends on your specific read patterns, write patterns, update frequencies, scale, and scale.
And understanding these nuances, the trade-offs we've discussed today, that's really your shortcut to being well-informed. It helps you make strategic decisions in this complex, fast-moving world of big data. It's about making your data work smarter for you, not harder.
Definitely. So maybe a final thought for you to consider. As these table formats continue to evolve and potentially converge even further, as we discussed, how might the role of the data engineer actually shift? Will it move away from managing the nuts and bolts of storage specifics, the low-level details, and move towards focusing purely on data intelligence, building robust applications, and enabling faster insights from the data? What new innovations might emerge when that underlying data layer becomes truly seamless, truly interchangeable across all platforms and tools? That's an exciting future to think about.